Should I start? Am I audible? And should I start now? Good evening to all. Am I audible? Okay, then I'll be starting. So today will be the second lecture on motor control for electric vehicle application. So already we have understood something about induction motor. So now we will learn slight in details about few technical parameters of induction motor and slightly in details, and also how to use the induction motor as synchronous generator, which has wide application in wind turbine as well as also in dynamic braking, regenerative braking. So when that motor is, say, one train is climbed on hill, and while it is coming down, so naturally the total potential energy what it was achieved by the train, so that will be spent to generate some electrical energy, and how it could happen and how experimentally it can be seen. All these things we will learn today. Okay, and one small simulation tool also, because that will be needed later on while we will be simulating the vector control and induction motor control, speed control, BLDC control. All these things will be required, so we'll have a glimpse on that also. We'll be doing that things in PSIM, not in Simulink or MATLAB, because MATLAB or Simulink basically needs some wider memory, whereas in PSIM it can be done very quickly. It's a customized application. Okay, so today we will be learning about the speed torque characteristics of induction motor as well as the concept of asynchronous generator. So we already understood what is synchronous, and why it is synchronous, it's called synchronous, and why it is asynchronous. So just conceptually, if you think from the instant when the motor is getting started until it is fully accelerated and reaching the rated speed, what is happening? Let us conceptually let us understand that. So basically, motor and transformer both are like, if you see the construction wise, both are very nearly equal, but the transformer having the common core, so that it is stationary. But for motor, so you can consider, for a motor, stator is the high voltage side and rotor is the low voltage side. Okay, but both the cores are different. Core are not coinciding with each other. So that's why that electrical energy in rotor, it is converting to mechanical energy. But the equivalent circuit and everything, they are more or less same for transformer and motor. Okay, so you see this side, the x-axis, this is the speed torque characteristics. It's very important. I am going very slowly so that you can understand it. So here your speed is 0, and slowly the speed is increasing, and here speed is equal to the synchronous speed. That means the speed at which the stator flux is rotating. So once you apply the three-phase power to the stator, immediately, as we learned yesterday, the stator space, the flux started to rotate. At that instant, your rotor is stationary. So the relative speed between rotor and the stator rotating flux is maximum. So number of flux line cut by the rotor is maximum. If that is happening, then your EMF generating in the rotor are very high, because it is d phi by dt. Suddenly maximum number of flux is cut by the rotor conductor. So high voltage is developed in the rotor. And already yesterday, from the construction of induction machine, we learned that the rotor bars are short circuited. So due to that, suddenly very high current will flowing through the rotor bar, which is causing high torque. So you see, during starting, so here is my rated torque. So my starting torque is higher than that. And once the torque is very high, it is accelerating. It is accelerating the machine. Why this nature? I am going to explain why this is. First more, then again up, and like that, why it is happening. Then once high torque is developed, then rotor started to accelerate, and once it is getting accelerated, then the relative speed between the rotating flux of the stator and the rotor is coming down. And once coming down, then it is again less voltage, and again it is less torque. And so first it is getting accelerated, okay, and then it is slightly coming down, and once it is coming down, again the relative speed between the rotor and the stator flux, rotating field flux, it is again increasing. Again maximum number of again more number of flux line is cut by the conductor. Again voltage high, again current is high, again torque is high. It is trying to again going up. So basically these things is continuously happening inside the motor. So first it is standstill, and once you are giving the power supply to the stator, immediately number of flux line cut by the rotor conductor is maximum, high voltage developed, which in turn flowing high current through the rotor bar, and again it is producing high torque, which is accelerating the machine and going towards the synchronous speed. Once it is slowly going towards the synchronous speed, again the relative speed between the rotor conductor and the stator flux is coming down. It is nearly to zero. So that time number of flux line cut by the rotor conductor is also minimum. So again your torque is minimum. So if torque is minimum, it is trying to retard it or deaccelerate, and once again it is retarded, then again the relative speed between the rotor and the stator flux is increasing, which is in turn increasing the torque and again going towards the synchronous speed. So these things is continuously happening inside the machine. Due to this reason, the induction machine never able to reach, this asynchronous induction machine is never able to reach or catch the synchronous speed. Okay, and due to this reason, till it is getting accelerated, it is drawing very high current. So if the motor is rated for current I, or say 10 ampere, one motor is rated for 10 amperes, till the motor is getting accelerated, normally it will be in the order of 2 to 3 seconds, the motor will draw around 50 to 60 ampere, 5 to 6 times of its rated current, which is called hot start. Because as you know, if the current is more, the heat produced by the stator winding also more, so which is called hot start or direct online starting. So naturally, to mitigate this criteria, if your motor rating is 10 kilowatt, you have to design a source, or you have to identify a source which can deliver 60 kilowatt for 2 to 3 seconds, because during the starting the current requirement is 5 to 6 times. So to avoid this kind of things, as well as continuous hot start may deteriorate the basic insulation level of the stator winding. So for medium voltage machines, it was recommended by the manufacturer that successive 3 hot start is permitted. Say I given the 1 hot start, immediately due to some process it is tripped, again I given, like that I cannot give continuously. Maximum 3 hot start is permitted. More than that, it will degrade the insulation level. Normally in medium voltage, the insulation class is F class. That insulation level, it is not included in this course. So to avoid this hot start and to introduce soft start, that variable frequency drive is required. That means it will never allow the motor to draw that 6 to 7 times current, which is called inrush current, but the machine will be capable to produce the rated torque. Okay, some way I can reduce the current, but it should not happen that my motor is incapable to accelerate the load. It should able to accelerate the load, as well as it should not take the inrush current for a long time. This is my requirement. So to mitigate this requirement, these variable frequency drives are introduced, which you will learn in details in our consecutive successive lectures. So the point when just the motor is started to accelerate and the torque produced by the machine, it is called the starting torque or locked rotor torque, because basically rotor is a standstill, so that's why it's called locked rotor torque. And this locked rotor torque is nothing if your one transformer secondary is shorted and if you are applying the rated voltage in the primary side. So what is happening, the same thing happened when your rotor is locked. Basically it is shorted. It is shorted, and due to that reason this high current is flowing. And the point where the torque is coming down is a minimum, this point is called pull out torque, which is denoted by pull up torque, PUT. And the point where the torque is maximum, it is called pull out torque or breakdown torque or the stalling torque. Now one very important question, how I will select the machine for my intended purpose. Okay, so if I draw a vertical line here, so the region of left side of this line is unsafe region. I cannot select. So normally say this particular motor will be used to drive a centrifugal pump whose system resistance curve is like this. Okay, is like this. That means this is the resistance offered by the pipeline to oppose the flow. And the point where intersect, this point is my operating point and this is my slip. This is quite good, but if I got a system resistance, if I got a system resistance is like this, that means where the things is intersect here, then this motor is not suitable for that purpose. Why? So when you will be working in industry, you are taking some project for some chemical or refinery or somewhere. So the first thing they will ask you to select the motor. They will give you this curve. They will give you this curve. They will tell you have to overcome this system resistance, and based on that you select your motor and make the data sheet and give it to us for approval. then how you will select? Then you have to contact with manufacturer, you have to give the system resistance curve, and you have to ask from them the speed torque characteristics, and the both the things to be superimposed. After superimposing, you have to see that your operating point is right hand side of this line. It should not be left hand side. Why so? Let us understand it conceptually. Say my machine is running nicely here, it is at steady state. Due to some reason, this point is the torque requirement, because the flow line, I don't know, anytime anything may happen, so it is shifted here. So if it is shifted here, so what will happen? From this point it is shifted here. Now my required torque is higher than the available torque. Okay, so sorry, my required torque, so here this my operating point is here, and due to some transient condition my machine shifted here away from this point, operating point. Now my available torque is higher than the required torque. If that thing is happen, my torque is more, so it will run faster. It will run faster to catch this point. It will come and settle down here. Another condition, if you take, say my point is shifted here, so that time my available torque is lower than the torque required. Say I need 10 kilonewton torque, but my available torque is only 8 kilonewton, so my machine speed will come down. So come down means, again come down means this side is speed less and this side is speed high. Okay, so again this point is shifted and coming to my operating point. So if my operating point is right hand side of this maximum peak, then whatever may be the condition, my machine by its virtue, this will be capable to bring the operating point at the desired level. But what will happen here? Say due to some reason, due to some electrical transient, my operating point shifted here, my machine torque shifted here. So now my machine torque is lower than the desired torque. So what will happen? It will start to deaccelerate, and it will come to lock rotor position. Lock rotor position means it will stop. Now say my another condition, my torque is here, my electromagnetic torque is here. So now my torque is higher than my desired torque, so it will run faster to catch that torque. If run faster, it will go towards this and it will reach the stalling torque. So for both the cases, if I choose the operating point at left side of that pull out torque, for both the cases either it is going to lock rotor torque, means the rotor is locked condition, or it is going to the pull out torque or the stalling torque, and both the cases my machine will stop. So it's a very unstable situation. It's well and good if the transient, if I can control the transient within 1 to 5%, it can compensate. But if that things is higher than that, if the electrical transient is higher than that, and suppose that variation is more and the operating point shifting more than 5 to 10%, then both the cases my motor will stall, which is not advisable. So to select the machine, always you have to superimpose the operating point, which should lie on the right hand side of the pull out torque region. Okay, why I given this took more time to explain this, because you are the student, maybe some professionals, I don't know, but when you will be working in the industry, so this is the very basic thing to select the motor. We are working for any purpose, for electric vehicle, for any other purpose, you should know that. Okay, so hope this I able to clear to you all. So this is the equivalent circuit of a separately excited DC motor. This is the field side which is producing the flux, everybody know it, and this is the armature current, this is the brush. Okay, now the torque produced by the machine is equal to some constant into this flux into the armature current. So this concept will be required to find out the torque produced by the induction machine. Okay, so that's why I have shown this equivalent circuit, and later on this is very much important to conceptualize the vector control, because in vector control we will be establishing the separately excited DC machine analogy to an induction machine. Basically that is the very basic things to understand vector control. As I was telling, the motor can be treated as a transformer. This electrical circuit is more or less same. So here you see the core is common, but in stator it is not so. Okay, so here you see this is the primary side or HV side or whatever maybe, and this is your secondary side, and this is the equivalent circuit. This part, this current I0, this is required to produce the magnetization. We will learn it later. Okay, and here it is the ideal transformer. This voltage E2 and E1, the ratio of, in case of transformer, this is E2 by E1, which is the turns ratio, N2 by N1, because this equivalent circuit will be, and this is the stator side and this is the rotor side. Because our torque is produced by the rotor, so to find out the torque, this concept of this circuit is required. Okay, so this is the, you just, everybody in your graduation, you have basic electrical machines, you have learned it already. Now I should tell what is the power frequency of the rotor, the current which is flowing through the rotor, what is the frequency? This is required. It is very important to know to calculate the torque. Ns, the synchronous speed, say for an instant, the power frequency, it is F, and the rotor frequency, rotor power frequency is F dot, and at that time the machine is rotating at RPM N. So the slip, the change of RPM from its synchronous speed is Ns minus N, which is already we have learned, that is 120. F dot, this is the rotor frequency, by P, and we know my synchronous speed is 120 into stator frequency by number of pole. Now if you divide these two things, this equation and this equation, if you divide, you will get like this. F dot by F is equal to ns minus n by ns, which is the sleep basically. So my rotor frequency is basically the sleep time of the stator power frequency. Very simple. So why it is required? Because in the equivalent circuit we have seen there is some reactance. There is some reactance is available because it is inductive. So there, you know, the the reactance for an inductance, it is depend on the frequency, correct? So I have to consider here in this frequency. So which will be sleep time of the power frequency. So to establish that, this is required. Now if you consider the torque equation of separately excited DC machine, which is proportional to, the torque was proportional to, I used one constant, torque was proportional to flux and the armature current. So in this case, the armature current, if you see the equivalent circuit which I have shown you earlier, that is I2, and this flux is proportional to the rotor voltage, okay, and that should be sleep times of the voltage E2 if you consider the equivalent circuit, and the current flowing through the rotor is ER by ZR. So as I told, it is rotor side, so it should be sleep time, okay. And this is the phasor, you know, this resistance of the rotor, and this is the total reactance of the rotor, and this is equal to, this is the hypotenuse, so square root of both two square. Here as it is DC, so there is no power factor, but this is AC, so that's why that cos phi 2 is involved here. So in this equation, if you put all those value, you will get the torque as this. Now there is a, because we are considering that things for single phase, so if you consider for three phase, so this constant will come. You know, everybody knows that the power is equal to the product of torque and RPM, and if it is RPM it is coming, so that pi n by 30, this factor it will be introduced. So that's why it is for three phase. So these are the things coming. Now the starting torque, so you see this is a function of sleep. Now from this is the equation for instantaneous torque. For starting torque, your sleep is what? Because that time your speed is 0. So basically sleep is n minus n, ns minus n by n. So if ns, so if this is 0, so your sleep is equal to 1. So in this equation, if you put your s equal to 1, the starting torque will be converted as this. Now if you want to find out the pull out, so now in that speed torque characteristics, I obtained these things from the previous slide, which is starting torque by putting s equal to 1. Now how to find out this and this? Because these are the extrema. These are some extreme point, maximum or the minimum point. Now if you take the instantaneous torque equation and this you differentiate with respect to, so if you differentiate this torque with respect to sleep, and equate it to 0, so you will get all the extremas. If you do that, then it is arriving R2 is equal to plus minus Sx2. If you put that, then your maximum torque, that means the pull out torque, this torque is converted as this. This you can check it practically. You can go to CGL or L&T or BHEL, these websites, and there you go to electrical machines. You will get the data sheet. From those data sheet you can able to get all those parameters, electrical parameters. It will be given there. Now you can open your MATLAB or Excel, whatever may be. So in your x-axis and your y-axis, here you take the x-axis as slip, y-axis as torque. You vary from 0 to 1 with one step of 0.001, and you equate the torque, and both you plot, you will get this kind of curve. Okay. Now the thing which I am going to discuss, that how, it's very important, how the motor can be used as generator, induction, because normally other kind of alternators, you need to give the field supply, excitation you need to give, but here excitation is not needed. It will be taken from the reactive power. Okay, so already these characteristics we know, it's the motoring region. And in generator it will be, because you know, generator, for generator mode torque is required, it will not deliver, torque is required, so that's why the torque is negative here. But you have to operate the machine more than the synchronous speed. So your slip is basically, your slip is synchronous minus your operating speed by synchronous. Now if here your operating speed is greater than synchronous speed, that means the negative slip. So if your slip is negative, that means this n is higher than that ns, then it will go to generating mode. And here this is the braking mode. You know, our electrical, say you take our locomotives, so they are first the electrical brake will apply, then it will slightly reduce, then the mechanical brake will apply. There will be thruster brake or electromagnetic brake, which will, there will be brake shoe. It is a spring operated. So slowly, then once, say the locomotives, the wheel is rotating at say 1000 rpm. So first the mechanical brake will be not applied, first the electrical brake will be applied, then slowly it will come down, and then your mechanical brake will be applied to stop the locomotives. This is everywhere for EOT cranes, and everywhere people will do this. So to make the machine on one induction machine, to operate one induction machine to generator mode, you have to operate the machine higher than the synchronous speed. And which position you have to do and all, that is that will be, I am not going in details of that, because that is there are some calculations are there. So at what sleep it should be, at what negative sleep it should be operated, all these things again, because we have, you have learned the stable zone and the unstable zone of the motor already, you have learned. So from there you can uh, calculate it. Now I am coming to the connections. Here, this is it is called overrun clutch. It's called mechanical overrun clutch or electrical. So this experiment was done by a group of students from, I think, SRM University. A group of students from SRM University to my lab. They have done this experiment. Okay. So this is the induction motor I want to use as generator. Here you can put definitely one energy meter to see. So first, what is again, and this is another motor whose rated speed should be higher than this synchronous speed of this motor. Okay, this is connected with one variable frequency drive. Okay, this is a VFD. Like this, and definitely in the non-driving end one sensor is connected. Okay, and this is the control of the VFD. This feedback is taken from the encoder. This is a shaft incremental encoder to measure the RPM. Say this machine, this is a 4-pole machine, so the synchronous speed is 1500. Or you can take, this is a 10-pole machine, for example, say it is 600. Sorry, 10-pole machine means 600. Okay, and you can take this machine, 4-pole machine, so this speed is 1500. Okay, say this machine, this generator, this induction machine will deliver the rated current push to the grid once the RPM is 650. Say for example, typical one value I am taking. So, and this control, from the control you have to give one feedback to the overrun clutch also. You can take a electromagnetic clutch, it is always better. Means normal position it will be de-engaged, and when one supply will go, then that clutch will be engaged. Now first thing is you de-engage the clutch, the sequence of operation. Okay, you de-engage the clutch to start the motor which will be working as a generator. Then 3, you make the control such a way that once the speed of this motor reach at 600, then you start this motor which will be driving the generator as same as 600. Once both the machine speed becomes 600, then you engage this clutch. So my synchronization is over. Now you slightly, through the variable frequency drive, you slightly increase the speed of this motor and go to 650. Now you can able to see that energy meter will be giving positive reading, opposite reading, that this machine is pumping the power to the grid. This is the experimental setup. Okay, so I think today's lecture is up to this. I will show you some within 1 or 2 minutes. This is the package where this is the PSIM. Most of the people will be knowing it. So this package will be used. I'll take only 1 or 2 minutes. This package will be used for simulating the VFD. So here will be whatever will be needed, I will be showing you. So this is the induction machine. So if you double click on that, here you can set all the electrical parameters. So I'll make the torque flag 1 so that I can see the electromagnetic torque. Then you have to give some source. You go to power, then you go to element, voltage, and this is the 3-phase line. So you give that 3-phase line. If you double click on this is the line voltage. You can give it to 415 because our grid supply for domestic is 415. So you can give it 415, frequency is 50 Hertz. And these are the things through which you can get the phase current. Okay, you can get the phase current. And this is the voltage sensor. You can put it here. So this will give you the voltage. You join it like this. Okay, you can join it. Now to sense the torque, mechanical torque, if you want to sense. So you see here mechanical torque, and this is the speed sensor. You can connect here. If you want to load it, so this is the load, mechanical load. Okay, now the torque sensor, you can again go to power. This is the torque sensor. You can connect it here. You can join it. And this is the probe. If you right click, it will rotate. These are the things. So here you can set it. This K1, K2, K3. I'll tell you later how the torque in generally it is represented in first order form or higher order form. So say you can take, this is a phase current IR, Y, IB, like that. This is the line voltage. And this is the mechanical torque. And this is the RPM. Now go to simulate, take the simulation control. Total time you say you can take it's 0.1 second. Now if you simulate, see all the parameter came here. We will check the RPM. So it will take slightly more time. So we will take 0.5 so that we can see it, because it's direct online starting. You see the machine accelerated in this way, and after that, because the machine is 6-pole machine, you see it's a 6-pole machine, so that's why it's 1000 RPM. Now if you if you want to see the electromagnetic torque, it is like this. So I'll show you how that from this, how you see, if you see that first is more, then coming down, coming and coming like this till the acceleration. And if you want to see the phase current, see, this is the phase current, as I was telling, the inrush current. So initially it is very high up to 0.1 second, and after that it is, once the machine fully accelerated, it's come down to its rated value. It's a no load current. Full load current will be higher. You can calculate that calculation, how to calculate the rated torque and all that I will show you one by one. So hope you have understood what I have told today. If you have any question, you can ask, or I can terminate the session. Would you like to ask any question, or I will stop? That I can download means your college might have it. Student version you can always download. What is the tool you are using for simulation? It is PSIM, Power Sim. Some of the PPT is invisible. Please rectify, sir. Yeah, I will try to rectify it. To improve the damping. Yeah, that everything I will, when the control, I will control aspect I will explain, there I will tell you. You see, normally for stable system, it's a thumb rule. It's a thumb rule. Always you should use the system as critically damped. It should be critically damped. How the damping factor is to be chosen, and how the, because these are the things will come into picture when there is a closed loop control. Correct. So based on the position of pole and zero, you have to marginally select the damping as well as the natural frequency. Then only next lecture discuss in Hindi, please. Oh, Hindi. Okay, that I have to. This is PSIM. P power SIM. That's why this damping, I will, how to improve the damping, that I will explain why when the closed loop control I will be discussing. Okay, because you see, when this question of this damping and all these things, it will come into picture, that time closed loop control is involved. And once there is a closed loop, okay, so you have to linearize the entire system. Unless, why do you deleted my message? I have not deleted anybody's message. I can't delete. I can't. First of all, I can't operate anything from here. I'm just saying, I don't know how to reply you. Software. That software is PSIM. Okay, the way you have to linearize the entire entire system. Unless otherwise you are linearizing the transfer function, you cannot tune it properly. BLDC motor can it can theoretically it can, but it is not advisable. It is same, more or less it is same. No, to control a DOL starter is not advisable. So for that it is a start delta, after that soft starter, and now it is VFD. That how that hot starting is converted to soft starting, I will explain this, and next time set the screen in a frame so we can see what you are writing. Oh, you can't, while I was writing you can't see, huh? No, this because there are lot of limitations are there. Okay. Have you seen anywhere for power? You how much which teach? Will you teach? Yes. Without transfer function, you cannot understand the vector control. In my channel also there will be some lecture series which is told about the dynamic high performance dynamic modeling of induction machine. You can search in my channel, and there also it is available. Actually Hindi I can discuss Hindi because I can speak in better in Hindi, but most of the people, because I am from Tamil Nadu, and here most so many South Indian people may be joined, so they are not familiar with Hindi, so I have not gotten the software name. Software name is PSIM. P for power, S for simulation, I for India, M for mango. Yes sir, it was out of the screen. Okay. Most of us don't speak Hindi. Yeah. Software name is PSIM. Okay, next time I'll also hear how to sign in to chat. All messages send appear publicly. This I will and at the end of this lecture series, I will this it will be taught such a way that after going the industry you should not face any problem. I know so many of my students when they are, yeah, ECSR college, how to find the required torque of, yeah, everything I will tell you. Yeah, you can use my laptop is very slow, so that's why I'm using that one. Yeah, that is PSIM. That is also very good software, but MATLAB is for so many things. Sir, can you use MATLAB? Yeah, you can use MATLAB, not at all an issue. Same blocks are available in MATLAB also. Degree BBA, I don't know. I want to quick summary of the today's class. Okay, so today we have learned about the speed torque characteristics, and as a prime mover how an induction motor can be selected based on your load characteristics. Then how to formulate the torque equation, and how one induction machine can be operated for asynchronous generator, and very few introduction of the PSIM tools. Yeah, I always explain you first theoretically, means pictorially, not theoretically. K value is constant for everywhere. I will tell you because time is not there. How, what is that? It is start if it is same only. That is a constant. K is a constant. So it is not dependent on any other condition. Okay. You see, these questions, these are the you see, there are a lot of limitations are also there. We have seen the star delta connection of the stator because you are talking about the motor capacity maybe within maximum 100 kilowatt. Can you tell me one delta connected motor of 1 megawatt? No, it is never. No designer, there is no necessity to design a medium voltage motor of 1 megawatt with delta connection. So so these are there are, I will explain one by one at the end of the lecture. Your all this question will be resolved. You see, I have the experience to design a motor of 10,000 kilowatt, 10.1 megawatt. Induction motor, I told na, induction motor primary should be a star or delta. If the delta is there, means the neutral point is not available, then what should be the primary winding is connected in preferably. I am not able to understand. No, star and delta, it is whatever the circuit I have drawn, that is a single phase circuit, one phase. So it is immaterial of star delta, only that value will change. Okay, whatever may be, it is a phase. So if it is a star, you convert into delta. If it is a delta, you convert into star. It's not at all a matter. I will explain. I understand what is your basic thinking and from where you are asking this question. But everything I will explain you. That circuit which I have drawn, it's a par phase circuit. Okay. My name is Shitangshu Shekhar Bishas. I think you are Bengali. Sir, if I want to do a industrial project on this, then is it possible? Yeah, it is very well possible. This I have made this course content so that you can, using this, you can approach to an industry. So for practical purpose, you can come to Pantech, where I will be teaching the entire control with commercial drive, and that time it will be, because these are the glimpse, I cannot tell everything here. Actually, slide how to share, I don't know. You can ask Mr. Malayappan, so that I can give him and he can give. This is the course name is motor control. Yeah, I am from West Bengal. I am from Calcutta. I graduated from Indian Institute of Science and Technology, Shibpur, Bengal Engineering College. Sir, can you share me your number? My my WhatsApp number is 9445072 948. I'm repeating once again. My WhatsApp number is 9445072 948. Sir, single line is not displaying. I don't know. Okay, next time onwards I will try to, because I am not that much expert in present PPT making and all. Normally it is done by my student. So due to lockdown it is not possible. I used to, now I am only making. I will try to improve that. And at the end of the course I will be showing you the industrial drive also, how to use it, how to program it, how to connect it, everything. Oh, in maintenance I have separate course with somewhere, but that is for purely departmental people. I will try to uh, conduct the course separately here in Pantech. So shall I terminate the session for today? Okay, so we will see tomorrow.